Hello. We are talking about power and energy today. You've learned about power and energy in physics class. You've learned about power and energy in Circuits 1. And today I'm going to present it in a little bit different way, hopefully a very practical way that you can use. I'm in my workshop, so we can do a demonstration to start the discussion. I'm set up in the workshop to measure power, and the power I'm going to measure is to my drill press right here. You'll see that the drill press it has no drill in it. When I operate it, it's going to be operating unloaded. I thought I would need to load it up. So as you can see, there's a block of wood under there, and you may be able to see the wood shavings. And I actually put a 1/2-inch spade bit in this, and then I drilled into the wood. The drill press draws a surprising amount of power when it's not drilling, and when I started drilling, it didn't draw much more than when it was not drilling. So that means that I have a very inefficient drill press. Efficiency, of course, we'll talk about that, is power out divided by power in. And I have a very inefficient drill press, and that is pretty much to be expected because it's a low-cost drill press. I paid less than $200 for it. And I don't use it a lot. It's very nice to have when I need it. I don't use it a lot, so efficiency was not my main concern getting it. To measure the power and energy to it, I'm going to swing over now to the meters that I'm going to be using today. And to start, I'm going to measure the voltage and current to the drill press. So the meter on the left is already set to AC voltage, and I have that one turned on because I like to know when the power is off or on to the circuit that I'm working on. So it's reading 2.24 volts right now. That is noise. The connection to this is an extension cord that is plugged into this outlet strip and goes to 2 banana leads that are going into the voltage inputs on that digital multimeter. So when I turn the power on, I get 122 approximately volts. As we go through these demonstrations, you'll see that varying. I've seen it vary from, I think, 118 to 125 as I've been working in here getting these set up. That's very common. The voltage on the power distribution system varies, and specifications usually are it can vary plus or minus 5%. And on a 120 volt system, that is 114 to 126 volts. So as long as we're in that range, we are getting the voltage that the distribution company guaranteed us. I won't work on a circuit when it's energized, so I'll turn the outlet strip back off, and I have actually checked those leads, checked the outlet strip, made sure everything is wired correctly so that when my voltage reads almost 0, 2.2, it is actually off. I'll connect to the outlet strip. I'll connect the plug for my drill press, so it's not working yet. I have here an extension cord with a 120 volt plug on it that also goes to 3 banana connectors. These are much better than the ones that are on the voltmeter because they're shrouded. And to actually come in contact with the conductors on those, I would have to try. I would have to stick a wire down inside those. So I like these much better. I've only had one of these made, so I'll use it on here. So I plug the extension cord into the outlet strip, and I'm going to pull it right back out because I should actually make the connections before I plug it in. I like to have as many open switches, open circuits between me and 120 volts as possible. The meter's telling me it's been on too long. It's going to turn off if I don't do something, so I turned it off and back on. I also checked the wiring on these leads. The green is the safety ground. We'll be talking more about that. The white is the neutral. These two are both connected to ground at the service entrance for our house. The red one is the energized conductor. That's the one that will be 120 volts above neutral and above earth ground. So to get the power to the drill press, I'm going to plug the energized conductor into the amp connection, the 10 amp connection on the other multimeter. I will set that to AC and DC amps. It's an auto-ranging multimeter. It detects whether it's AC or DC. I don't have to tell it. It's an auto-ranging multimeter, but you set the AC or DC from this button. This is a new multimeter. So that's the energized conductor. Then I have the other part of the extension cord also with shrouded leads on it, and I will plug the drill press into this. The drill press is plugged into that. The energized conductor from this will be plugged into the common on the multimeter. So remember, current, to get current to the drill press, we need an almost zero impedance path. And that zero impedance path, low impedance path, is through the ammeter. Ammeters allow current to flow. Voltmeters are almost open circuit, so very high impedance here where I'm measuring voltage, very low impedance here where I'm measuring current. That allows the current to pass through. Now I have two other leads left on the two connectors. I will connect white to white with a connector that's designed to connect two shrouded leads, and I'll connect green to green. Now I will plug the 120 volt plug into the outlet strip. Turn the outlet strip on. We're back to close to 122 volts on the ammeter. We're reading 8 milliamps flowing to the drill press, and the drill press is turned off. There is a light on the drill press, which I turned on. Now we're reading 133 milliamps to the drill press. Turn the light back off. Everything is off. I'm going to turn the source off again, and we go back to zero. So it appears we actually have some current flowing to the drill press while it is turned off, which is not an unusual thing. There is some leakage current in almost anything that's connected to the 120 volt system. So we have 7 milliamps flowing there, probably in capacitive coupling inside the machine itself. We could track that down if we needed to. It's not a concern here. Now I'll turn the drill press on. You may be able to hear it. I don't know if you can hear it or not, but it is running. And we know it's running because we have current flowing. And the current we're seeing is 2.02, rounding it off, about 2.02 amps and 120 volts. Notice that when I turn the drill press on, the voltage drops. When I turn it back off, the voltage comes back up. Turn it on, the voltage drops. Why? Because the current's being pulled through the outlet strip, through the wires, and when that current is being pulled through those wires, they have resistance, impedance, and you get a voltage drop across that impedance, and it causes the voltage to actually drop to the drill press. So here we have 120.6 volts and 2.04 amps. I'm going to write that down. So I'll write down that the voltage is 120.3. I usually round these off, and it's bouncing around. To know exactly what we can write down accurately, we'd need to go to the specifications for the digital multimeter and see how accurate it usually is. But usually if you're using a meter and you round off the last digit, you'll be okay within the accuracy. We are going to talk about metering accuracy during the class, just not today. So there's 120. I'm just going to call it 120 volts. That seems to be where it is now. Current is 2.04. Just going to look at it and write it down. 2.04 amps. So we're talking about power right now, and then we're going to talk about energy. So, is that the power? And let's go to a different color here. Power is equal to VI, right? Power in watts is equal to volts in volts times current in amps, right? Oh no, this is AC. We need this other thing, cosine theta. We're going to talk more about that cosine theta and calculating reactive power, but not today. We just want to deal with real power today. So how do I get real power? We need to measure that phase angle theta. Before we do that, though, let's look at a different way to measure the current. Right now, I have the current going through the ammeter. And that's fine, but often you're measuring a circuit that's wired in. It's hardwired in, and you don't want to break the circuit to run it through an ammeter. So what do? We had electricians here at our house last week, and they were installing some recessed lighting in our kitchen, and they had one of these. And it's a clamp-on meter, clamp-on ammeter. This one's very nice because it will clamp on to AC or DC. Most of them do AC only, but I got these for the lab because we need to measure both AC and DC. So it's 30 amp maximum, clamp on. How do you do that? I'm going to remove the ammeter from the circuit because we're not going to use that anymore, and I'm not planning to use ammeters anymore in this class. So power is off. Shrouded connectors. I'm protected. I'm just going to connect the energized part of the circuit together. So now I have a closed circuit. Nothing measuring the current. Turn the power to the circuit back on. Drill press runs, but I don't have I don't have a meter to measure the current. Now I connect the clamp on ammeter. I open the clamp. I clamp it around the wire. I set it to AC amps. And this one's not auto ranging. I can set it, I'll set it to 4,000 milliamps since I already know that it's about 2 amps. Put it somewhere we can see it. Okay, we can see it in the circuit. And now turn this one off. I'm through with it for now at least. Turn the power back on. Turn the drill press on. And we are reading there 2,150 milliamps, so 2.15 amps. That's how we can measure the current in the circuit without actually breaking the circuit, which in power and energy applications is often very important. We still need to measure the phase angle so that we can calculate the real power. One way to do that is using an oscilloscope. And I have a very nice handheld oscilloscope here. The voltage reading, I'm sending the voltage to channel A, and I have another extension cord with banana plugs plugged into common and channel A. To measure the current, the oscilloscope only measures voltage, so I need a way to measure the current. The old way to do that was to run the current through a very precise, very small resistor, so 1 milliohm or less, and a very precise resistor, and then measure the voltage across that resistor and use Ohm's law to calculate the current. Now, instead of doing that, we'll use another current clamp. This is the only way to measure current. It's the best way, and it's the way to measure it when you're doing work like this. So, where the clamp-on ammeter is, I will also clamp on this current clamp. And now the oscilloscope is measuring voltage on channel A, current on channel B. Turn the power to the circuit back on. Turn the light on the scope. I think we can see that. You're seeing the voltage waveform, the 120 volt waveform. Interesting thing about it, when we do power factor, I'll take a picture of this so we'll have something good to work with. The top of that sine wave is flattened off. That's because of all the DC loads we have in this house. And a DC load, any electronic load, is a DC load. It starts off with a rectifier and rectifies the AC to DC and then powers the load. So that's any electronic load. Now, that's not what we're here to talk about today. I will turn the power to the circuit back on. Turn the meter back on, but what we're really interested in is that oscilloscope. Now, we can see the voltage and the current waveforms, and what I am seeing is that they are almost 180 degrees out of phase, which means I connected the current clamp in reverse. You can look on the current clamp itself and it will tell you which is positive and which is negative. I usually connect it, and if it's 180 degrees out of phase, then I just turn it around like I just did. Now, we've got the current and the voltage almost in phase, but they are not in phase. If you look closely at this, you can see the peak on the voltage waveform is here. The peak on the current waveform is there. When we talk about power factor, we'll use that and we'll actually calculate power factor. But all I'm going to use it for today is to say no, they are not in phase, because I'm going to measure the power a different way. And the way I'm going to measure the real power is using this device, which is a watt meter. I'll show you what the back of the watt meter looks like. I have another one here. And the back of the watt meter looks like this. Input voltage, output load. These are very nice devices to use. Now, the downside is you have to break the circuit, because you put the input voltage here, you connect the load, in this case, the drill press on the other side. There's an internal shunt that measures the current, but then it displays watts for you. I have other watt meters, actually energy meters, that use current clamps instead of actually running the circuit through the device. And those are the more common ones to use. This is a lab device, and it's the one I'm using today. It's very convenient to use, and I'll show you why. So, power is off to the circuit. I'm through with the oscilloscope. That's definitely a way you can measure real power, but it's not the most convenient way. So I'm going to set it, just stabilize it. I don't need the current clamp. I do these things. I like to have the circuit as simple as possible. So I'm going to unplug the drill press from the extension cord, and I'm going to plug it into this other outlet strip. There are too many wires here. That is what happens in the lab. I like to minimize wires, but even on this fairly simple setup, there's still a lot of wires. The outlet strip is connected to the output side of this watt meter. The input side of the watt meter is connected to this plug. So the watt meter is plugged into the 120 volt circuit. The drill press is connected to the output of the watt meter. This is a very convenient way to measure power. Now I'll turn the circuit on. I'm going to set, I have the meter, right side it measures voltage or current, left side measures watts, real power. We have some disagreement between the digital multimeter and the watt meter. The disagreement may be within the error of the two devices. One of them may not be calibrated very well. They're actually coming closer together. But we'll call it 123 at this point. Amps flowing very low, almost nothing, because the meter's not turned on, the drill press is not turned on. Watts flowing, showing -2. Turn on the drill press, it does not come on because I have too many outlet strips. Turn this one on, turn the drill press on. Now we have watts, 194 watts, 2 amps flowing. That 2 amps flowing is what I was talking about when I started this. This is pulling 2 amps when it's not drilling. And when I drilled, it went up. I was drilling hard into that wood with a 1/2-inch spade bit, and it was getting up to maybe 2.4 amps. So it's a very inefficient, very high loss device. Let's write these down. Using the watt meter. What's the power? Our furnace just came on. It is in this room. That pulled the voltage down to 117, 118. But regardless, we'll use the power that it's showing now, 188. So 187, 188. Real power, P, is 188 watts. That's what I'm going to call it. I'm going to shut everything down, and we will go to do some calculations. That's the real power. If we'd calculated V times I here, we would have gotten around 240. That is volt amperes. That is apparent power. And we use the abbreviation S on that, but we're going to talk about that more on the complex power day. For now, 188 watts real power. That's instantly. When I turned that off, it went to zero, very close to zero. Let's check that. Let's look at that one more time. Power showing -1, -2. That's within the meter's error. When I turn everything back on, instant I turn it on, it goes up to 180 plus watts. When I turn the drill press off, it goes to zero. On, 186. Off, zero. Power's instantaneous. It's what that drill press is drawing right now. Energy. Let's see, let's make that statement first. Power is instantaneous. Energy is over time. What's the definition of energy in this case? We can write an equation using, oh no, calculus. Power as a function of time. Integral of power as a function of time dt. Integrate power over time and you have energy. And what are the units on energy? Joules, which is a watt second. You can do watt hours, common in energy industry, kilowatt hours, megawatt hours, gigawatt hours. You'll be seeing all of those. I like kilowatt hours. That's what we generally do when we're talking about something the size of a drill press. So kilowatt hours. What's P of T in this case? Does it change over time? Only if I turn the power off. So if I leave the power on, the energy is staying fairly constant. It's changing a little bit. It changes with the voltage, but I'm going to say the power is 188 watts. That's power as a function of time. Okay, let's put when that happens. When drill press is on, only then. What's the energy? 188 watts times, well, we have to integrate it, 188 watts dt. When we integrate that, when we do that integral, it becomes 188 watts times the time. So if we allow the drill press to run two hours unloaded, can't think of why we'd do that, but if we did it, the energy would be 188 watts times 2 hours, which is 376 watt hours, I believe, or 0.376 kilowatt hours. That's power and energy.